using molecular orbital theory, predict which of the following species has the shortest bond length. Now what you want to do is you have to use the molecular orbital theory and you have to predict the bond length, right? Now how can you predict the bond length? You are using molecular orbital theory, so there is a term that is called as bond order, right? Bond order. Now what is it, students? Bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons right, and that is divided by what? That is divided by 2. Okay, so your bond order is inversely proportional to the bond length, right? So more is the bond order, shorter is the bond length. So what we need here is, we need to find out the bond order first. How will you find out the bond order? For that you'll have to write the number of electrons in the bonding and anti-bonding molecular orbitals, right? Now say for oxygen O2 2+, how many electrons will be there on total? O2 2+, there will be there are 16 electrons in O2, right? And O2 2+, there will be how many electrons? 18. Now let's write its molecular orbitals. We'll have sigma 1s2, sigma anti-bonding 1s2, sigma 2s2, sigma anti-bonding 2s2. Now as it is oxygen, so what will come here? It will be sigma 2pz2, then pi 2px is equal to pi 2py, that 2 and then is there 18 now? 2, 4, 6, 8, 10, 12, 14, right? And there will be then pi anti-bonding 2px2 is equal to pi anti-bonding 2p by 2. So it is 2, 4, 6, 8, 10, 12, 14, 16 and 18. Now we have got 18 electrons, right? So what will be the bond length, students? Now we have got here sigma anti-bonding 2pz, which is vacant. So the bond order will be equal to number of bonding, that is 2, 4, 6, 8, 10 minus the anti-bonding ones 2, 4, 6 and 8. So it would be this, that divided by 2. So what we will get? 2 by 2, the bond order is 1 over here. Now what is the next species given, students? It is O2 plus, right? So students, I think I have committed a mistake here. It's O2 2+, means there are 2 electrons less, not more. I have increased it. It should be 14. I'm sorry, students. I'm really sorry. It should be 14, right? So there would be 2, 4, 6, 8, 10, 12 and 14 till here only, right? And these electrons won't be present. I'm so sorry, students. It is O2 2+ and I made it like I increased 2 electrons. I should have decreased it. So the number of bondings would be, it should be 2, 4, 6, 8 and 10, and the anti-bonding electrons would be, there will be 2 and 2, 4. So here it would be 4, right? So 10 minus 4, what you'll be getting here? You'll be getting here 6. So 6 divided by 2, you'll be getting what? It would be 3, right? So the bond order for O2 2 plus is 3. Then we have got what? Then we have got O2 plus. Here the bond order is equal to 3. Now here what will be the thing? It would be 15, right? So the number of bonding is 10. Number of anti-bonding would be 5 divided by 2. It is 2.5, right? Now O2 minus. O2 minus, what will be the thing? Let's take out for O2 minus again. O2 minus. So there will be 17 electrons. So it would be sigma 1s2, sigma anti-bonding 1s2, sigma 2s2, sigma anti-bonding 2s2, sigma 2pz2, then pi 2px2 is equal to pi 2py2, right? Now we need to have 17 electrons. So pi anti-bonding 2px2 is equal to pi anti-bonding 2py1. Is it 17 now? 2, 4, 6, 8, 10, 12, 14, 16 and 1, 17. So what will be the bond order here, students? The bond order will be equal to how many bonding electrons? 2, 4, 6, 8 and 10 minus the anti-bonding ones 2, 4, 6 and 1, 7. So this is 3 by 2, that is equal to 1.5, right? So students, this thing for O2 minus, it is the bond order is 1.5, and O2 2 minus, how many electrons would be there then? 18, right? So your O2 minus, so if it's 18, it would be how much? 10 minus 8, 2. So it would be 1. The bond order will come out to be 1, right? So which has the highest bond order here? Oxygen 2 plus, O2 2 plus. So which will have the shortest bond length? O2 2 plus, right? So students, do remember one thing here, that if you are writing these molecular orbital energy levels till nitrogen, what you'll do, sigma 2pz comes after pi 2px and pi 2py because of mixing of s and p orbitals. But for oxygen and fluorine, there is no sp mixing, and sigma 2pz comes before pi 2px and pi 2py. Right? What happens in nitrogen and other smaller elements like your carbon, like boron, the s and p orbitals are close to each other. So as the result of which, what happens, that there is mixing, and the energy of s orbital, that is 2s orbital, is further decreased and at the expense of 2pz orbital. It increases the energy of 2pz. Because there can't be mixing of pi orbital and sigma orbital. So there can be the mixing of sigma and sigma, right? So this was your question. It was a bit lengthy question, but you can just write the configuration for one and can predict the bond order for the others also.